Hello, lovely human. Jen Foxbot here. Welcome to another edition of a Math Mondays Neural Networks. Huzzah! So, in this series, we look at the mathematics behind large language models, which power things like ChatGPT. So cool. So, in this episode, we are going to take what we learned from our intro to neural networks when we looked at a simple architecture or basically a way to build a neural network with just 3 layers, 3 pieces of data going in, 3 inputs, 3 neural network buddies in our second layer, and then our output layer, which gives us our hypothesis or prediction function. So we are going to generalize this to all sorts of neural networks of different shapes and sizes. Yay! Okay, let's get started by quickly reviewing what we learned. So each of these input nodes is going to map to each of the neural nodes in the next layer. So lots of arrows to show that. Yay, arrows. And then if you're like, what about our bias node? Heck yeah, we got one up here. So this will also map to all of them. Oh, I'm so lazy. I'm like, do I have to draw all the arrows? Yes, I probably should. Thank you for motivating me. And then we have our hidden layer of artificial neurons, which are represented with A's. I got excited and drew smiley faces in them, but now I feel like I should label them. So this is A1 in layer 2. This is A2 in layer 2. Sorry, smiley faces, you're still there. This is A3 in layer 2. And then there's also a bias node, A0 in layer 2, and all of these map to our output node in pretty purple, and our output node gives us our prediction, and so there's just one. Oh, well, I'll just label you above. Okay, so this is A1 in layer 3. And yes, there's also a bias node here, so A naught in layer 3. Okay, and when I say A naught, I mean A subscript 0. It's a thing I learned in physics that I just picked up without even thinking about it. Okay, so this was the simple architecture, but it's just one type of architecture. And to be good data scientists or just good knowledge enthusiasts, we want to learn how to generalize to any size or shape of neural network, especially because neural networks that make up large language models are huge, like ridiculously huge, a lot bigger than 3 layers and 3 of artificial neurons. However, I did recently learn from a colleague that they have actually used a simple architecture like this to recognize handwritten digits, which is so cool. It's kind of one of those like AI projects that you can do if you're really enthused about it and or just want to learn how they actually function, which is a great way to do it. Learn by doing. Huzzah. Okay, so anyway, let's generalize this. And if you know me, you're going to be like, are you going to draw a picture? And heck yeah, we're going to draw a picture. So I'm going to draw kind of a little bit of a larger neural network. I'm still going to, it's hard to generalize to, infinity and all of that good stuff, or just below infinity, but we'll do our best. Okay, so we are going to have our inputs x1, x2, and then I'm going to draw dots, dot, 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 all the way to kind of represent, and then you keep going. And then our last one is going to be x subscript n. So we have n number of x's. N could be 3, or n could be 45, or it could be 145,000. Okay, cool. Just there to hang out and let us know that there's some number of nodes, because we're generalizing, right? Okay, so, wait. Then we said this is layer 1. Layer 1. Still our input layer. Okay. And then we have our artificial neurons. So similarly, I'm going to do some circles to represent the nodes, but I'm lazy, and so I'm going to draw 2 and then a dot, dot, dot. So this is A subscript 1 in layer 2. I wrote a 1 instead of 2. And then A this is our second artificial neuron in layer 2. So A subscript 2, superscript 2, and then all the way down to A In layer 2, it's going to have an M. So this could potentially be a different size in length. We could have more or less artificial neurons in layer 2. And similarly, we can have another layer, dot, dot, dot. Now these are getting small and they're hard to label when they're small. So in this third layer, second hidden layer, lots of numbers floating around, we have our first node in layer 3. We have our second node in layer 3, and then we have our last node in layer 3, which we also want to represent with a variable. What do you think? Is it going to be something we've seen before or something entirely different? Something different. Yeah, it could be the same size or it could be a different size. A lot of times what you will see is neural networks that kind of go like this. Like they start small and then the number of layers gets, they start large and the number of layers gets smaller as you go. Okay, so you could have any number of layers in between layer 3 and the output, but clearly I'm running out of room. And so then we get to our output neuron, and there's just going to be one of those, because if you are trying to make a prediction, you only want one prediction. Well, and that prediction is associated with a probability, but you kind of only want one of those, because it would be confusing if you talk to ChatGPT and it gave you like 2 sentences that were smushed together or something like that. And so this is going to be our output. This is going to give us our hypothesis function, our prediction, and then we'll label this with a layer, oh goodness. Well, in this case, it's just going to be layer 4, and this is going to be our first node. But I guess theoretically, if we wanted to generalize appropriately, I would put a letter here or something to represent that this could have many different layers before it got there. But I don't want to be lazy, so whatever. Okay, and then if you're like, where's the bias? Where are the bias buddies? Bias buddies, I like that. We will have those as well. So for each of these layers, I'll have bias nodes for layer 2 as well as for layer 3. A naught layer 3, and then for our output as well. So a naught in layer 4. Okay, cool. All right, so now that we have a picture to help us generalize, I'm not going to draw the arrows because it makes it messy, and I like it clean. But you map each of the nodes to all of the other nodes, which we would do with linear algebra. Okay, so let's look at how to generalize this. So for layer J, we're going to look at the second layer because that layer is a little bit special. The last layer is also special. I should label that layer 4. So, but we'll generalize after we look at the second layer. So for layer J equals 2 and some node K, our variable for that artificial neuron is going to be represented by a z. And you're like, wait a second, why z? That's our sound of, hey, wait, let's refresh very quickly. So the sigmoid function is the, oops, sorry, I just hit the mic. I got really excited. The sigmoid function is the basis for neural networks. I was for all of AI. No, not necessarily. But for the architecture for large language models, yes. For neural networks, yes. Not necessarily for all of AI, because whatever, but okay. So our sigmoid function is g of z, where z is our input variable, and that equals 1 over 1 plus e to the minus z. And because if you're like me, you're like, what does that mean? We draw a picture. Yeah. Okay. So this is where our prediction comes out of, basically, which is like, and kind of when we talk about how activated or how turned on the node is, it's basically like what is the value of the sigmoid function for that particular node. And I always mess this up, but it's something like that, where this is 1. So as for higher values of z, the sigmoid function goes to 1. I should label my axes. For lower values of z, the sigmoid function goes to 0, and it crosses the x-axis at 1/2. So that is the same z here. Okay, I lost my piece of chalk. Hey, there we are. Okay. Okay, so now that we did our little aside in the sigmoid function, let's write out our generalized equation for our variable z per node k, where one of these little buddies is node k. So it equals our first parameter theta for that node. And because it's our first parameter, it gets a little 0 subscript. And because it's in layer 1, it gets a superscript. Okay, so this would be layer 1. Okay, so yeah, okay. So now we have that multiplied by our bias unit. I was just thinking in real time. Thank you for bearing with me. Okay, so then we add our second parameter theta k for node k in layer 1, and then we multiply that by x1, and this is in layer 1. Okay, I'm actually realizing that these should be 1. And then these should be 2. Sorry about that. Notation is important and confusing sometimes. And then this should be 3. Okay. And basically it's it's called layer 1 because it is, well, the first layer, but then this gets labeled with a 1 because it's like your first layer that you're calculating. I think I'm kind of hypothesizing here, but bear with me. So what we are doing is we are calculating the equation for this first node in this first neural network layer. And so that is going to equal a parameter, which is some number multiplied by every single input. So we have our bias unit, then we have our second, or like our first data point, and then we're going to have our second data point, x2. So it's going to be plus, we're going to wrap around because I ran out of space, plus theta k comma 2 times x2 in layer 1. And then we're going to go all the way for each input node, but because we want to be lazy, we're going to do dot dot dot, and then plus theta k comma n times x to the n for layer 1. Okay, and so we can represent these in vector notation, where we have x equals all of our input variables, so x0, x1, x2, dot dot dot, x to the n. X2 got really small there. And similarly, our variable z can be represented. We're going to have a variable z for each of these. Oh, wow, I have a lot of chalk on me. I love chalkboards, that's cute. We're going to have a variable z for each of these nodes. Okay, so for a particular layer j, that is going to look like this. So z, we have our first variable z in layer j, we have our second variable z in layer j, and all the way down to z of n for j. Okay, so this is for this special layer where we have the data input going in. But what if we have, what do we do for subsequent layers? What do we do for layer 3? Or if we have more layers of artificial neurons, what do those look like? Okay, and so now once we've kind of gotten away from the special case of this first layer, we can say for any layer of j, z of j, for a particular node, it's the same thing, but instead of x's, we have our artificial neurons. Huzzah! And because we have that, we want to kind of generalize and say, oh, sorry, it's not j, it's j minus 1, right? Because for the current layer, your inputs are the previous layer, or 1 minus the current layer. So similarly, it's going to be a naught for the previous layer, and then we just update these superscripts accordingly. So this is going to be a 1 for the previous layer, and la 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 la, we just erase some things and generalize all the way. So j minus 1, a 2 of j minus 1, and lastly, ooh, that 1 is really big. Oh my goodness, sorry, my fingers are getting coated in chalk and it's really hard to erase. Okay, and then finally for that last artificial neuron of n. Okay, cool. So that's your generalization, and I forgot to close that. All right, so la 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 la. We can basically then say that the equation for a particular node, we'll just say node k, equals the sigmoid function of that node, or j plus 1. Wait, sorry. J. Well, yeah, okay, there we go. That works. La, 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 la. Because we have the same notation here. So this feeds into our node. There we go. Okay. Sorry, it's easy to get confused with all the J's and K's and L and N and M's around here. It's like your alphabet soup. Okay, but basically you need to calculate your variable z so that you can plug that into the sigmoid function to calculate what the value of your node is. Basically, like, what does it equal on a scale from 0 to 1? How much is it activated? How much does it play into the next layer? Because if your node is close to 0, it's not gonna impact the next layer as significantly as if it is 1. La 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 la. Okay, so what is the last thing that we want to talk about? So basically, and just our sigmoid function is applied element wise to vector z, which basically means, like we did in the and example, you sum up all of the z's for that particular node. You sum up all of the parameters for that particular node, and then you calculate the sigmoid function for that sum. So you do it inside first, calculate the sigmoid function, and then you get your value of the node. And I believe in the next video we'll do a couple of more examples. I think that's where I want to go next before we move on, because this stuff is like, what the heck, is confusing. The one last thing, bear with me, we're almost done. So the one last thing is our special output layer, the last layer. And so that one is actually way simpler because, hey, it's just one output node. So for layer, I'll just say, oh wait, let's use purple. For layer last, node k, our hypothesis function is going to equal a j plus 1, which is going to equal the sigmoid function of z of j plus 1. Cool. So yes, that's it. Okay, that feels really. I'm like, oh, are we done already? Okay, I guess that's it. But yeah, so basically, what's really interesting is that you do all of this complex math, and at the end, you kind of get just one prediction, one value from 0 to 1, and you're like, oh, that's it. But there's actually a lot of complicated stuff happening in the background. Um, and our hypothesis function can have many, many, many parameters in it. So that's kind of what's hidden in here, is that we have a matrix, capital theta matrix. And in this last one, it will just be one row because, well, there's just one theta. And then it's multiplied by all of these values. Okay, so that was a lot. Generalizing notation is usually a little bit complicated. I hope that was helpful. Please let me know if you have any questions. Please double check me. I am reviewing notes from many years ago, so it's like jogging my memory as I'm teaching. So yes, happy to answer any questions. Please let me know if there are particular areas that you want me to dig into. I think it makes a lot of sense to do some examples like we did last time with the AND gate application with the neural network. I also gave you some homework, and maybe we'll run through that so you can check your work on the OR gate application. Cool. But yeah, let me know if there's anything else that you would like to learn. I can't make any promises, but I will try. Thank you very much for hanging out with me while we work through this. I will see you next time, my dear friend. Goodbye.